Okay, so next talk is Transport and Accretion in Planet-Forming Disks, presented by Geoffroy Lesur.
You hear me? Wow, fantastic. So good afternoon, everybody. I was given the quite tedious task to present the problem of transport in accretion disks from the theoretical side. So this is a chapter led by Neil Turner, and the co-authors are Sébastien Froment, Charles Gamy, Hubert Klar, myself, Mark Wardle, and Xuning Bai. So, because, as I told you, this is mainly a theoretical talk, I should start first with a disclaimer, which is that absolutely no computer was harmed during the simulations I will present in this review. That being said, I should point out that it's not true for the people who run the simulations. Now, let's go through the outline of this talk. So I will concentrate on class 2 objects, so mainly disks around T-Tauri stars. First, with a very broad introduction to the problem of transport in disks. Then I will talk about MHD processes, and in particular, the well-known magnetorotational instability. I will then do a short review on gravitational instability, and then I will explore a few novelties, so to say, which are hydro instabilities in disks, and I will try to make some connections with observations. So let me first start with the problem we are looking at, which is the problem of transport. Essentially, the problem we have here is that we want to accrete material on the central object. And if you want to accrete material, you have to somehow evacuate the angular momentum you have in the bulk of the disk. And that's been a long-standing problem. It's been here since the 70s, essentially. And if you just assume you do that through molecular viscosity, obviously you get very low accretion rates, orders of magnitude lower than what you see in T-Tauri stars. So the problem is clearly, what is transporting angular momentum? How do you have accretion in these objects? And the thing I will try to present here are different mechanisms through which you can have accretion in these objects. So the first kind of class of mechanism is the turbulent transport kind of model, which is quite well known. It's the alpha disk model. I think everybody here knows about that. This thing has been suggested in 1973. That's Shakur and Soniev. And essentially, the idea behind this model is to say you have a sort of turbulent mixing length theory, which is quite similar to what you have, for example, in convection layers in stellar models. So what you do is you say that your angular momentum is transported inside the disk by some sort of fast viscous process. So it stays inside the disk, and you define a turbulent transport, nu-t, which is proportional to the local sound speed times the disk thickness, which is h. And you have this dimensionless parameter, which is the dimensionless measure of the viscous transport, of the turbulent transport, and typically, from observation, you expect alpha values, which are between 10 to minus 3 and 10 to minus 2. So that's the first class of process, and that's the thing many people use. Now, it turns out that you can have a kind of different kind of process, which is driven by winds. So in this case, the angular momentum does not stay inside the disk. It's evacuated on both sides by a wind. So essentially, the idea is that the wind is exerting a torque at the surface of the disk. It's slowing it down so that you have accretion in the mid-plane. So this thing is essentially driven by magnetic fields, and something you have to remember is that this kind of accretion process is not described by an alpha disk model at all. So that's the two main classes of accretion mechanisms, and now we'll turn to the first class of processes, namely MHD processes, starting by the magnetorotational instability. So we've heard about this instability a bit this morning. This is a cartoon showing you how this instability works, just a sort of qualitative understanding, physical understanding of what's going on. So let me consider a vertical magnetic field line threading the disk vertically, and I have two fluid particles attached to this field line, A and B. Now I will assume that I'm going to move one fluid particle inward and the other fluid particles outward, and the two particles will be still linked to the magnetic field line. So what will happen if you do that? Well, the particle which has been moved inward will try to conserve its angular momentum, right? So since it has been moved inward, it's going to move faster. So it will drift forward compared to the reference point, and the particle B will do exactly the opposite. It will drift slowly, so it will drift backward. So now keep in mind that these two fluid particles are still connected by the magnetic field, which means that you have a sort of spring linking the two fluid particles, and A will be slowed down by the magnetic tension, and B will be accelerated by the magnetic tension. So that if you slow down this fluid particle, it will move further down toward the star, whereas B will move further away in the outer disk. So typically, this mechanism is a runaway mechanism in which you will get quite strong instability, which is technically the magnetorotational instability. So in this picture, I've used the fact that the two fluid particles were linked, tightly linked to the magnetic field line, and that's the ideal MHD approximation. Now, as I will show later, it turns out that disks are not in the ideal MHD approximation, and because of that, I will allow fluid particles to drift across field lines, and of course, you can expect that then this mechanism will be much less efficient or even suppressed in some situations. So, this instability has been studied for quite a long time now. The first simulations were done in 1995, and I'm going to show you a typical MHD simulation. So these are the main properties we know of the MRI in the ideal MHD limit. So typically, we can say that global simulations in which you compute the whole disk, and local simulation in which you just look at a tiny box inside the disk, all of these simulations are consistent with each other, and they all give typically values of alpha, which are typically between 10 to minus 3 and 10 to minus 2, which is exactly what you want to explain accretion rates. Now, if you look at an actual simulation, this is a global simulation performed by Mario Floch, whom I thank for the movie. So this is what it looks like. So this is a global disk, 2 pi disk, and that's computed between 1 and 10 AU. And here we are looking at the turbulent velocity. So typically, you have here about 9 scale height, and this thing creates quite well-developed turbulence, which is typically the picture one have in mind. For disks, you have subsonic turbulence in the midplane, about 10% of the sound speed, mildly sonic turbulence in the upper layers, typically 0.5 times the sound speed. This thing is magnetized, so you can compute the magnetic plasma beta in these disks. And you have essentially a corona in the upper layer, which has a beta of the order of 1, and lower betas in the midplane, typically about 100, 1,000 in the midplane. So you have a magnetized plasma, which is turbulent, which creates a quite efficient angular momentum transport, and this is it. We have the answer. So from that point, you might think, well, it's done, the problem is solved, and we should all go to the pub and have a beer. It turns out that, as usual, if you start digging, you start finding dead bodies. And in the case of the magnetorotational instability, we have not 1, not 2, we have 3 dead bodies. These are the known ideal effects we've heard about yesterday, I think. The names are Ohmic Resistivity, Hall effect, and orbipolar diffusion. So why are these things important? They are important because the ionization fraction in the bulk of the disk is typically about 10 to minus 13. That's very small. And these effects in this situation are very important. So what are these? Ohmic resistivity is essentially the collision between electrons and neutrals. Hall effect is an effect which is associated to the drift between your ions and your electrons. And orbipolar diffusion is the drift between neutral species and electrons. Now, these are words. You might ask, well, which effect is dominant in which part of the disk? And this plot will tell you the answer. So that's taken from an annual review paper by Phil Armitage. This is the density in the disk. This is the temperature. And this blue line is essentially the location you would expect in a typical T-Tauri disk in the mid-plane. So up there, you are at 0.1 AU, and you are here at 100 AU. So what you find here is that in the mid-plane, in the inner regions, you are dominated by ohmic diffusion. If you go further out, you are dominated by Hall effect and ambipolar diffusion in the outer layers. Now, if you are high up in the atmosphere, so typically 4 scale height, you are entirely dominated by Hall and ambipolar diffusion. So that's the two main messages you have to get from this plot. Here, ohmic diffusion in the inner region, and then Hall and ambipolar diffusion. So first, I'm going to concentrate on this inner region, which is dominated by by ohmic diffusion. In this region, we have already a problem, which is called the Prandtl number crisis. So what is this? This thing is, so this Prandtl number compares ohmic diffusion time to viscous diffusion. So of course, this is molecular diffusion. So this viscous diffusion is very, very small. It's a tiny number. Ohmic diffusion, on the other hand, is quite large. So this Prandtl number in protoplanetary disk is typically very small. It's like 10 to minus 5, 10 to minus 6. Now, if you try to perform a numerical simulation, you can only perform their simulation in a range of Prandtl number between 0.1 and 10. And in all the simulations up to now, which have been trying to compute exactly what's going on for PM, you find the same trend, which is that alpha decreases as you go to small PM. So it turns out that your disk is down there. So God knows what is the extrapolation of this thing for PM equal 10 to minus 5. So the answer here is that we have no idea what is the turbulent transport in a disk in which ohmic diffusion is dominant. The second point is related to the dead zone concept, which we've heard about. So to understand that, we have to take into account the sources of ionization in accretion disks. So you essentially have 3 sources of ionization. Thermal ionization, which is dominant in the inner part of the disk, below 1 AU. Then you have X-rays and far UV coming from the central star, and these things are able to ionize only the surface layer of the disk. And finally, you have cosmic rays, provided that they manage to penetrate the wind and the magnetic field structure around the star. And these cosmic rays are able to ionize the outer parts of the disk, typically above 10 AU. So in between here, you have this region in the mid-plane, in which, well, you have no source of ionization apart from radioactive decay. So this thing has been called a dead zone because you have essentially no ions, so the MRI cannot exist because here, this thing is done by ohmic diffusion. So this has led to the concept of layered accretion, which is quite old. It was presented first by Charles Gamy in 1996. And the idea is the following. You say that you have the MRI active in the upper layers, which are ionized by X-rays and cosmic rays. In this thing, you have accretion in the bulk of the disk, in the outer layers, and then you have accretion at the surface of the disk, and nothing really happens in the mid-plane. Now, if you remember what I was telling you about this non-ideal effect, in this upper layer here, in this plot, you are up there. You are in this region where ambipolar and Hall effect dominates. Ohmic diffusion is negligible in this upper layer. So people have been trying to understand what's going on in this active layer, including ambipolar diffusion. And the result is a bit worrying. So this is what we find. If you now take into account ambipolar diffusion in a dead zone, you find that essentially the MRI totally disappears from the disk. You don't even have an active layer. You have nothing. So this is what you have with ohmic diffusion only. That's the old picture with an active layer. You have activity at the disk surface, which enables accretion, and alphas, which are typically 10 to minus 3. Now, with ambipolar diffusion, you get essentially alpha, which is 10 to minus 7, 10 to minus 6. So the MRI is dead. Dead zones are really definitely dead. So of course, this thing relies strongly on FUV ionization, the presence of PAH, chemistry, etc., etc. So to compute these results, Xuning and by the way, there is a poster, 2S049, describing this sort of thing. So to compute these results, Xuning has been using a quite complicated chemical network involving something like 2,000 reactions. So this is quite accurate. But keep in mind, there are many effects hiding there. So, well, that's a problem. So people have been wondering, well, whether or not Hall effect can play a role to kind of reactivate the dead zone. And that's an idea which was suggested by Mark Waddell and Raquel Salmeron in 2012, which is that Hall effect could revive the dead zone because the Hall effect somehow managed to enhance the magnetorotational instability. So this has been looked into by Matt Kunz and myself recently, and we found that indeed the MRI exists in situations where you would have no MRI without Hall effect, except that the MRI does not produce turbulence. It produces something which is quite surprising. So this is a classical MRI picture in which you have 3D developed turbulence. Now this is the same thing with Hall MRI. What do you get? You get large-scale structures. This thing is linearly unstable. This is the MRI, except that it does not produce turbulence. The bad thing is that this configuration produces a transport which is like 10 to minus 5. So, well, Hall effect revives the MRI, but it does not produce any transport. Don't worry. We will find another way. So, let me turn now to disk winds. Disk winds, it's an old idea again. The kind of typical picture of disk winds was shown by Blanford and Payne in 1982. So typically, this is what we need. We have an accretion disk in which now I have a mean field coming from somewhere else outside of the disk. This mean field is threading the disk. And because you have accretion in the disk, the field lines are bended like that. So now if you assume that the field is strong enough so that the field behaves as a rigid wire, then the fluid particles which would be attached to this field line will be able to escape just because they are accelerated by a centrifugal effect, which we call the magnetocentrifugal acceleration. So this thing, to get this thing, you need essentially a mean field, and you need to incline the field by an angle which is larger than 30 degrees. And finally, to get the field line behaving as rigid wire, you need to have a quite high magnetic field strength, which is quantified by this beta parameter, which should be of order 1, at least at the in the launching region. So people have been wondering whether or not the magnetorotational instability and large-scale winds could coexist. And recently, we had 2 papers showing that actually the magnetorotational instability could naturally evolve into a disk wind. So these are plots showing here this is vertical direction, radial direction, and the tubes are field lines. So you see that's only half of an accretion disk, so that's the upper half. And you see that you have a configuration where you get inclined field line, just like what you have in the Blanford and Payne kind of picture, except that after some time, this thing becomes unstable, and you still have ejection, but the thing is quite unsteady. So this is a kind of turbulent Blanford and Payne picture, in which you have a disk wind, but this disk wind is variable. So this could be a precursor of variability in jets. So that was for a quite strong magnetic field in the mid-plane, and people have been wondering what happens for much weaker fields. What much weaker fields mean beta, which are 10 to the 3, 10 to the 5. So it's been shown in 2009 and subsequently that as soon as you include a mean field in all the simulations, you can create a weak magnetoscientifically driven wind. So the first paper was Suzuki and Inutsuka in 2009. And now if we get back to the dead zone problem, remember, we had no MOI, nothing at all. Well, if you now include a mean field in there, you have no MOI, but you can get a disk wind. And that's been shown by Xuning Bai and Jake Simon. This is the kind of picture one gets. The blue line is the magnetic field line. So essentially, in this region, in the bulk of the disk, the field lines is totally uncoupled. It doesn't see the matter. And then, around 4 scale height, you get the ionization front. And suddenly, you get coupled to the magnetic field line. And here, you can start a jet. Well, not a jet, but at least a wind. And here you go. You create your jet just at the ionization front. So this thing tells you that you can have accretion, typically with mass accretion rate of 10 to minus 8. So in a sense, you can still have accretion, except that it's driven by wind, not by turbulence. So this looks like a quite pretty picture, you know. But there is a big but. And the big but is that all the simulations were computed in boxes. And the problem with these boxes is that some quantitative results, including, for example, the mass loss rate, depends on the box size. And that's a problem, because it means that we don't really know whether or not these winds are real or not. So that leads me to my conclusion slide regarding MHD processes. So as I've shown you, the magnetorotational instability is likely to be largely insufficient or even totally absent in large parts of protoplanetary disks, typically between 1 and 10 to 30 AUs. So these results, of course, depend crucially on non-ideal effects, which means that you depend crucially on chemistry and radiation. The Hall effect will probably not save the MRI. And finally, there might be a way around these problems, which is to invoke some form of very weak, magnetoscientifically driven wind, though this has to be confirmed using global simulations because of these artifacts I was telling you about. So the future in this field is global simulations, including both the magnetorotational instability and large-scale wind. So I now turn myself to more hydrodynamical processes, starting by gravitational instabilities. So we've heard about these instabilities earlier, so I won't spend too much time here. So as you know, gravitational instabilities, the criterion for gravitational instabilities is given by this Q value, which was found by Tumre in 1964. And essentially, you say that you become gravitationally unstable whenever this Q is of the order or smaller than 1. So in a T-toy disk, you will get a Q value smaller than 1, provided that, well, the temperature is small, so namely the sound speed is small, and you have a large enough surface density, and omega is small enough, which means that technically you have to be in the outer parts of your disk, typically above 10 AU. So that's the criterion to get the gravitational instability. Now the question is, what is the outcome of the gravitational instability? Do we get turbulence? Do we get clumps? What do we have? The outcome depends on the cooling timescale, which is tau c. So if you have a large enough cooling time, then you can imagine the following situation. You are in a situation where you are slightly unstable, so Q is slightly smaller than 1. Then the system will become unstable, you're going to create giant spiral arms, shocks, and these shocks are going to heat up the gas. If you heat up the gas, you will increase the sound speed, and you will jump to a value of Q slightly larger than 1, so that you will switch off the gravitational instability. Then cooling will take place, CS will go down, and here you go again. So you can manage to self-regulate the disk so that Q stays always around 1. And that's described by this gravitoturbulence picture, which is shown here, for cooling timescales which are sufficiently long. Now, if you say that the cooling is fast, then there is no way that heating due to shocks will reheat the disk. And in this case, what you have is essentially fragmentation. These are the two big bodies you have here. So if you say you are in this situation, which is a long enough cooling time, then you have this nice gravito turbulence, and you can predict, based on simple equilibrium argument, what alpha is. And alpha essentially depends on the adiabatic index and the cooling timescale. So that's quite simple. That's a nice picture. It tells you that typically, well, if your cooling time is shorter than about 3 local orbital frequency, orbital time, then you are in the fragmentation regime, and otherwise you are in the turbulent regime. So that was a picture in 2001, and recently this idea has been challenged by 2 people, well, at least 2 groups of people. It turns out that the fragmentation condition, this critical cooling timescale, depends on the numerical resolution and is stochastic. That's really bad news. So what do we have here? That's a paper by Mero and Bate, 2011. These are SPH simulation of self-gravitating disk. We have horizontally the number of SPH particles, vertically the logarithm of the cooling timescale. What you see is that in this gray region you have fragmentation. And as you increase the number of SPH particles, then you can have fragmentation for longer cooling time. And there is no hint of convergence. That's bad news. It tells you that, well, we don't quite know what is the critical cooling timescale for which we get fragmentation. The second surprising result is this stochastic fragmentation shown by Samian Pardee-Cooper recently. So the idea is the following. If you pick up a disk with a given cooling timescale, with a given surface density, and then you take like 10 disks, exactly the same disks, same surface density, same cooling time, then for some of them, you will get fragmentation. But for some others, you won't get fragmentation. The reason for that is that sometimes you will get fluctuations in density and temperature which are strong enough to trigger fragmentation. And you only have a probability of going into fragmentation. And the longer you integrate their simulations, the more likely you are to run into fragmentation. So the conclusion of all that is that in the end, gravitoturbulence might not be long-lived. And it might be that actually, as soon as you are in a self-gravitating regime, then if you wait for long enough, you will always have fragmentation, whatever is your cooling timescale. So these are the conclusions on that problem. So as I've shown you, the outcome of the gravitational instability is still quite uncertain. It depends on the resolution. You can have stochastic fragmentation. There are other ideas which I don't have the time to discuss, which are the problem of convergence for different kind of cooling function, even if you consider radiative transfer shown in these 2 references here. So the last part of my talk will be dedicated to the forgotten or often forgotten hydrodynamic instabilities. The first of which is the baroclinic instability. So this baroclinic instability is driven by the entropy gradient you have in the disk. So technically what you need to get this instability is to have this beta parameter, which depends on the entropy gradient. This beta should be larger than 0. And then bang, you get it. Provided that you have the right cooling, you have the right heating, and provided that you heat the disk sufficiently strongly. So these are quite strong constraints. But then, if you have all these conditions, you can have vortices forming everywhere in the disk. You get a disk which is populated by vortices. They are everywhere. So this is a typical simulation of Peterson et al. And there's black thingies here are vortices. So this thing, because you have vortices, you will generate spiral density waves, and the spiral density waves will transport angular momentum. And these are the typical values of transport of angular momentum you get as a function of beta, which is this thing here. And you see that you get typically values of alpha between 10 to minus 3 and 10 to minus 2, which is exactly what you need. So this picture, of course, has problems because, well, it produces vortices, and I know that vortices are quite interesting ideas for many of us. Now, vortices are quite complex, and we have several examples of vortices in the Earth's atmosphere which undergoes quite complicated physical process. And it's the same thing in accretion disks. So the first problem is that vortices are always unstable in disks. So instead of thinking of a vortex like a big laminar structure, you have to think of it as a sort of turbulent structure. Secondly, you can have 3D circulation. This is well known. For example, in atmospheric science, if you look at cyclones, they undergo a 3D circulation in which you have vertical motion in the heart of the vortex. And that was shown in the context of accretion disk by Eloise Meyer et al. And finally, vortices can migrate. Just like planets migrate, vortices migrate as well. And that's an example of the radial velocity of a vortex in a typical accretion disk in which we've looked at several power laws for the surface density. So typically, if you say that Q is positive, which is the most reasonable approximation, then you find that your vortices will always migrate inward on a quite fast timescale, which means that if you have a vortex, well, the vortex will migrate, and you will have to regenerate your vortex, something else, in the outer layers of the disk. Another candidate, which I think is quite relevant, is the so-called Gsf instability. So that's not known in the disk community because this instability is actually found in stellar interior, especially in radiatively dominated zones. So this instability is essentially driven by the presence of a vertical shear in the disk. This vertical shear is driven by thermal processes. So typically, if you assume that you have a locally isothermal disk, which means that the temperature depends only on the cylindrical radius, then you get this instability. So I'm going to show you a picture done by Richard Nelson. So that's typically the evolution of a disk. This is pure hydro. This is radius. This is a vertical direction. And you see that you get something which looks like turbulence. So this thing here produces an alpha, which is again of the order of 10 to minus 3. So these are 2D. I think this is a 2D, but they also have 3D simulations showing the same kind of thing. So this thing is, again, I repeat, this is driven by the vertical shear, which is driven by thermal processes. So what do we conclude? First, that all the hydro instabilities we have at hand at the moment are driven by thermal processes. So in order to assess their existence in disk, we have to compute precisely the heating and the cooling we have in these disks. The other point is that vortices are very interesting because we know that they can trap dust, and we kind of see, as I will show later, we see something which look like vortices. So maybe this is a very interesting hypothesis. But keep in mind, there are uncertainties regarding their evolution on long time scale. They migrate, they are turbulent. Now let me turn to, quite briefly, to observation of transport mechanisms, starting with this vortex idea. So this is the paper by van der Marel, which have been discussed already earlier. So they see essentially a non-axisymmetric structure, which is the density of dust, millimeter-sized dust, at about 63 AU, and you don't see any of a structure if you look at very small dust grains. So this is felt to be a good indication of a vortex lying at 63 AU, and the model they present to explain this thing is to assume that there is a giant planet. So that's one of their simulations. The planet is this white cross here, and this planet clears up a gap. So this is a very big planet. It's 10 Jupiter mass. It clears up a gap, and at the edge of this gap, the outer edge, you have a vortex, which is created. And this vortex is located at about 40 AU in this model, assuming an alpha, which is quite small, 10 to minus 4. So to me, well, it's not entirely satisfactory, because you create this vortex at 40 AU, whereas this thing is located at more than 60 AU. So an alternative hypothesis would be to say that these things are actually baroclinic vortices. And this will be confirmed if it turns out that there is no planet in the inner region or no big gap. The second evidence we have of this kind of transport processes in disks, at least in stellar interior, is this paper by Narita et al. Showing here the spectrum of V1331 Cygni, showing lines of water, and this is CO. And essentially, the model, which is the red dashed line, requires the presence of a 4 km per second line broadening, which could be the signature of sonic turbulence in the disk. This paper as well, this time in the outer part of this by Geoffroy et al., so they look at transition of CS in dm tau, and this time they also find signature of turbulence, which is roughly speaking 50% of the sound speed, which is quite compatible with any scenario. It could be a vortex, it could be turbulence. So what to conclude? It seems like we have good evidence now of non-thermal broadening of spectral lines, which are probably due to subsonic motion. It could be turbulence. It could be vortices. It could even be the base of a wind. We have also indication of large-scale vortices. I should say I'm not entirely convinced by the planet scenario, so I am willing to consider other kind of scenarios. The perspectives are in higher resolution observations. I won't mention ALMA, don't worry. And the hope is that higher resolution observation will make the distinction between small-scale structure, so typically turbulence, and large-scale features like vortices or wind. Now, if there is anything you have to take from this talk, it's this big picture. So what do we conclude here? We have essentially three kind of zones in disks. In the inner layer, you are dominated by ohmic diffusion. I've told you this quantum number problem. We have no idea what is the alpha in this layer. Then, between 1 and typically 1030 AU, you have a magnetically dead zone. Nothing happens. The MRI does not exist there. So you can have a magnetocentrifugally driven wind at the disk surface, which can drive accretion, or you can also have hydrodynamical processes inside the dead zone. In the outer part, you can have the MRI, and you can also imagine having self-gravity in the outer disk. So you clearly see that the main bottleneck we have in transport theory is this dead zone. So 3 questions. Is the dead zone really magnetically dead? And the only way to answer that question is to improve the chemistry we have in here. The second question is, are these global wind really real? So we have to compute this global wind model, including all the non-ideal effects, Hall, ambipolar, and ohmic. And finally, we have to go beyond simplistic thermodynamics if you want to know whether or not these hydro processes are actually active in disks. And I thank you for your attention.
Okay, so it's time for discussion. Okay. You.
Hi.
Mark Krumholz, UC Santa Cruz. So I was a little confused by your treatment of gravitational instabilities in that you seem to be posing an opposition of gravitationally driven turbulence that would give you transport versus fragmentation. And my question is, why are those mutually exclusive? Why can't you have fragmentation that does produce some level of objects and also have transport? That is, in fact, exactly what we see happening in galactic disks, and it's what happens in the simulations of massive stellar disks, too. You get both transport and some level of fragmentation. They're not mutually exclusive.
Yes, but the level of transport you get is quite small. So I don't know what is the precise value of transport you can get, and I assume it depends quite crucially on the cooling you have in the disk. The thing is, if you look at the local simulation in which you see, for example, stochastic fragmentation, you find that as soon as you start to form fragment, the transport drops down by several orders of magnitude. That's the kind of evidence we have. But these are local simulations. So you can imagine having still an active layer somewhere in the disk and fragmentation in another region of the disk.
What seems to be the case in the sort of galactic scale simulations and the massive star simulations is that actually the amount of transport you get once you start getting fragments depends on, it's not as simple as an equation of state, but it depends on things like the characteristic temperature of the disk, or the ratio of the scale, how big is the scale?
Precisely, yes.
And so it's okay.
Yes, well, yeah.
Okay, so upstairs.
Okay, this is Ana Gómez de Castro from Complutense University, here at the top.
Yeah.
So I want just to point out that if you have this jet basis over there, the gas in the jet is going to absorb the X-ray radiation from the star. And then the photoionization of the disk surface will not be as efficient, and the models that people is managing these days around, they will not work the same way.
I agree.
We did some calculations back in 2003, parameterizing the analytical model of these winds, and we found out that for mass loss rates about 10 to the minus 9 solar masses per year, there was no X-ray flashes, there was nothing reaching the disk surface.
Right.
Okay.
Yes. Well, I guess it depends on the mass loss rate you assume in the jet, right? I mean, in the wind. So yeah, I agree.
Okay, yeah.
Daniel Price from Monash University. So just a comment on what you call improving your chemistry. So from the disk formation perspective, what we'd really like is for the resistivity to go up to help us form the disks, but you seem to be wanting the resistivity to go down to help you drive any kind of accretion in the disks.
Yes.
So it seems that improving your chemistry is going to make life difficult for somebody else.
Well, possibly. I mean, there.
But I agree that there's a very big uncertainty here that would be very interesting to sort out.
Yeah, no, I agree. There can be also dynamical effects, like, for example, you can imagine having reconnection layers in these almost dead zones, which could locally ionize in the reconnection layer the disk. So you can also have dynamical effects, but these are highly speculative.
Yes, Ralph Pudritz from McMaster.
Yeah.
Your region 3, when you have possibly MRI active,
Yeah.
it's an interesting point that when you have MRI, even if it's there, the lever arm for such a turbulent torque, it's only a fraction of the scale height of a disk, maybe
Yeah.
a tenth or less.
Yes.
Whereas any disk wind, even for a weak field, would be a few times that disk radius.
Yeah.
So there's a factor of 30, 50 difference in the lever arms of the torques.
Well, it should be of the order of H
yeah.
over R.
So even if MRI were active, if the field is still reasonably weak, the jet could still dominate, even if MRI is active below. So a real question then becomes, how extensive is the disk wind possibility on the disk? And
Yeah.
I don't think we have an answer to that yet.
No.
Just interested in your
No,
reaction.
I totally agree with that point. And actually, Xuningbai and Jake Simon have shown that at like 30, 40 AU, then you can have both MRI and light winds, and it's actually the mass accretion rate is dominated by the wind. So yes, yes.
Okay, so last question.
Edward Worobiev from Vienna University. I just want to comment on the first question regarding the self-gravity and fragmentation.
Mm-hmm.
So the problem with these local box simulations, they are short time, but if you see that fragments actually occur in the disk, then if you try to run it for a long time, global simulations, you will see that they start migrating into the inner regions. It's a very fast, very efficient transport mechanism because fragments are relatively massive. They quickly bring mass from hundreds AU onto scales of 1 AU. And that's,
Yes, but
that's something that is missing in short-term simulations.
Yes.
It's also confirmed in purely theoretical calculations that this mechanism should occur.
Now the fragment should survive down to 1 AU, which is quite uncertain because these things are light. I mean,
Yeah,
so,
they may not survive there. They may be accreted and dispersed, but that's at least that efficient,
Yeah.
very efficient transport mechanism from hundreds AU scales onto 1 AU scale.
yes.
Okay, so please thank the speaker again.
Okay.